Well, let's see what happens for the second derivative here. If I want to take the second derivative of the function, if I want to take the derivative of the derivative that I just calculated, that's not too bad at all. F double prime of x is going to be equal to whatever I get from applying the differential operator d on dx to the quantity x plus 1 all times e to the power x. And my strategy is exactly the same as before. I'm going to break down into smaller pieces, and as long as I can calculate derivatives of those smaller pieces, I have the formula for the derivative of the whole function. The derivative is going to be x plus 1 all times d on dx applied to e to the x, and then I have to add on e to the power x times d on dx applied to the quantity x plus 1. Well, hey, those are both pretty simple. I already know derivative of e to the x. I hopefully am comfortable with derivative of x plus 1. So I put my pieces back together and I say that this derivative must be equal to, well, x plus 1 all times e to the power x plus e to the power x times 1. Well, let's factor those e's out. And the e's of this computation, leaves me with x plus 2 all times e to the power x. My first derivative gave me x plus 1 all times e to the x. My second derivative gave me x plus 2 all times e to the x. If I kept going here, let me say that the third derivative is the derivative of the second derivative. The fourth derivative is the derivative of the third derivative, and so on. Usually in this class, we'll stop at 2, but there's not a reason why we couldn't continue. And in fact, those higher derivatives become important in different applications. It's fine enough to use the triple primes or the triple apostrophe here to indicate third derivative, but at 4 and up, that gets a little cumbersome, so we just swap that out for f superscript parentheses 4 to stand for the fourth derivative. Well, if I actually calculated those derivatives out, I would expect to see an x plus 3 all times e to the x for the third derivative, x plus 4 all times e to the x for the fourth derivative. So that pattern should be that for the nth derivative of this function, I would get x plus n all times e to the power x. Maybe your x is 2, maybe your x is 2 million, but hey, now we can calculate the 2 millionth derivative of a function. How cool is that?